Today, we are going to discuss in detail the second order perturbation for non-degenerate case. Already we have seen first order perturbation. It is continuation of that lecture. Before going into this lecture, kindly refer my earlier lecture on first order perturbation. Here I am going to explain the second order perturbation in a very simplest manner. We know the Schrödinger equation, when Hamiltonian act on the get vector psi, it gives the eigenvalue E multiplied by this get vector psi. And in first order perturbation theory, we have seen the total Hamiltonian can be separated into two parts. One is H naught, unperturbed Hamiltonian. The other one is H prime, perturbed Hamiltonian with a lambda parameter. I have explained the importance of lambda parameter in my lecture on first order perturbation theory. Now you replace this. H can be replaced by H naught plus lambda H prime, and the state vector can be written as a linear combination with lambda parameter. I have taken only first three components because we are interested in a second order perturbation. So the H naught plus lambda H prime, which act on the n0 get n0, that is unperturbed state, plus n lambda n1, that is uh, first order perturbed state, then plus lambda squared second order perturbed get vector for second order perturbation. So which is equal to en 0. This superscript 0 represents the uh, order of correction. This is zeroth order. That is unperturbed energy state. Uh, Plus lambda En 1. This one represents first order energy correction. Similarly, lambda squared En2, that is second order energy correction. Then multiplied by this three state vector, which I have shown in the left hand side. So now, in the case of first order perturbation theory, we have seen that we have equated the powers of lambda. Here we are going to equate the powers of lambda squared. So first you take H naught, then lambda squared. That is H naught lambda squared. So this can be written as H naught N2. That is get vector of second order perturbed energy. Then next is you take lambda, maybe I will use different color, lambda H cross multiplied by here lambda N1. That will become lambda squared. So we can take this parameter which comes with the lambda squared. So H prime act on the first order perturbed state, that is get n1. Similarly, you take right hand side. In the right hand side, en0, that is unperturbed energy state. Here lambda squared, you have lambda squared here. So En of En0 get N2. Similarly, what about En1? Here En1 lambda, here N1 lambda. So which will become lambda squared. So this can be equated, that is En1 multiplied by which act on this get vector n get n1 here. Similarly, the third term, let us take here also you have lambda squared. So this lambda squared n not get n not unperturbed state, nth state, unperturbed nth state, that is en to get n0. So now you take the inner product with bra n0. So you take first one, uh, First one, you will get N0, inner product of N0 with H naught. N0, H naught, N2 plus N0, H prime, N1. Then En is a number you can take out of the inner product. So this will become N0, N2. Similarly, the second term, En can be taken out as its number. So this will become N0, get N1. Similarly, the third term, En2 can be taken out and N0 with the inner product of N0 with the N0. Now we will simplify this. Now we got this expression. We will analyze one by one. First, you take this term. Since H naught is a Hermitian operator, it will act on either bra vector or get vector. If it act on the bra vector, then you will get En0, the inner product of N0 with N2, which is exactly same as first term of this. So both will get cancelled. Then what about here? The second term, this is unperturbed, unperturbed energy state. This is perturbed energy state. So naturally, this inner product will be 0. What about this N0 with N0 inner product? Due to orthonormal property, this is equal to 1. So in the left hand side you have, sorry, right hand side you have En2, that is second order energy correction, which is equal to here only this second term left, that is N0 H prime N1. So you can see if you compare with the first order perturbation, you can see in which the first order energy correction is, that is first order energy correction we have seen is equal to N0, that is the expectation value of perturbed Hamiltonian in unperturbed state. But here it is not the case. So N naught H prime N1. Then from the first order perturbation theory, we know that get N1 is equal to, we have seen, summation over when M is not equal to N, M0 H prime get N0 divided by En0 minus Em0 multiplied by this get vector M0. Now you can replace this here. That is here N1 prime, you replace this one. So what you will get is, I have shown that parameter in the bracket. Summation over M is not equal to N uh, M pra M0 H prime get N0 divided by En0 minus Em0 get M0. So we got this, and actually this is N0 bra N0 H prime and this N1 prime. N1 prime only we have replaced. So we got this expression. Now you bring this bra vector and H prime inside the bracket. So this will become the second one. This will become N0 H prime M0. So if you take complex conjugate of this, that is the bra vector and get vector get interchanged. So this will be equal to M0 H prime N0 exactly if you take complex conjugate. So it is equivalent. So you can take modulus square of this numerator, that is modulus square of M naught H prime N naught modulus squared divided by En 0 minus Em0. So this is second order energy correction. Now M is not equal to N. You know why M is not equal to N. I have explained in the first order perturbation theory itself. If m equal to n, then this will be 0. This will shoot up to infinite. So which is unacceptable solution. So this is the second order energy correction. If you compare the first order energy correction, where as I said, En1 is equal to bra n0 h prime n0. So this is actually the expectation value of perturbed Hamiltonian in unperturbed energy state. So here you can see in the matrix form, these bra get vectors are matrices. Bra vector is row matrix and get vector is column matrix. So n both. So row and column are same. That is H prime for first order perturbation is diagonal element in the matrix. And in the second order, the matrix elements are off diagonal element because M is not equal to N. So with this understanding, we will move further. We will see the detail in the next lecture. Thank you very much for watching my videos and supporting me continuously. Thank you very much.